Welcome back, everyone. Today on The Explainer, we are jumping straight into what is honestly one of the greatest scientific detective stories of all time. We're taking a journey that starts with ancient philosophy and takes us all the way to the absolute mind-bending realities of modern physics. And the goal? Discovering the fundamental building blocks of the universe. We're going to explore exactly how a few brilliant minds armed with some incredibly clever experiments peeled back the layers of reality to reveal the hidden structure of the atom.
Now, for centuries, literally centuries, we thought the atom was absolutely unbreakable. In fact, the word atom itself actually comes from the Greek atomio, which translates to uncuttable or non-divisible. It was considered the absolute smallest piece of matter possible, period. But what happens when we prove that long-held belief wrong? How does a massive scientific paradigm shift actually happen? Well, it happens in the laboratory.
Section 1. Smashing the indivisible atom. So, our timeline kicks off way back around 400 BC, with those early Greek philosophers coming up with this idea of the uncuttable atom. And honestly, that idea just sat there. It was completely dormant for over 2 millennia. It wasn't until 1808 that a British schoolteacher named John Dalton finally put atomic theory on a firm scientific basis. Though, to be fair, he still viewed the atom as this ultimate, solid, spherical particle. But the real crack in the foundation, that appeared in the 1850s. Michael Faraday started studying electrical discharge, and he showed that electricity itself seemed to have a particulate nature. The indestructible atom was definitely about to meet its match.
Section 2. Discovering the electron. Okay, let's dive into this. Towards the end of the 19th century, scientists started tinkering with high voltages in these really strange evacuated glass tubes, and this directly led to the device that shattered the indivisible atom, the cathode ray tube. By pumping almost all the gas out of a glass tube and hooking up a massive voltage across 2 metal electrodes, scientists saw this glowing stream of particles. These cathode rays shot in straight lines from the negative cathode to the positive anode. But here was the real game changer. These rays behaved exactly like negatively charged particles, and their characteristics didn't change at all, no matter what gas was in the tube or what metal they used for the electrodes. This definitively proved these particles, electrons, were a basic, fundamental constituent of all atoms.
By 1897, the brilliant British physicist J.J. Thomson decided he needed to actually measure these things. By applying both electrical and magnetic fields perpendicular to the path of the electrons, he could literally bend their trajectory. By perfectly balancing those fields and measuring the deflection based on the charge, mass, and field strength, Thomson calculated the exact charge-to-mass ratio of the electron, and it was a staggeringly precise figure. 1.758820 times 10 to the 11th power coulombs per kilogram.
But wait, it gets better. Let's see how this builds into an even more precise measurement. In 1906, R.A. Millikan stepped up with his completely ingenious oil drop experiment. He sprayed an incredibly fine mist of oil into a chamber, ionized the air with X-rays so the droplets would pick up an electrical charge, and then, this is the crazy part, he used an electrical field to literally suspend the falling oil droplets in midair. By doing this, he was able to deduce the exact fundamental charge of a single electron, negative 1.6 times 10 to the negative 19th coulombs. And by combining that with Thomson's ratio, they figured out the electron's mass is an infinitesimally small 9.1 times 10 to the negative 31st kilograms. Just impossibly tiny.
So here's the puzzle. If atoms are packed with these tiny negatively charged electrons, but the atom as a whole is electrically neutral, what does the whole thing actually look like? Well, in 1898, J.J. Thomson proposed what he called the plum pudding model. You can also think of it like a watermelon. He envisioned the atom as this spherical pudding of uniform positive charge with the negative electrons just embedded inside it like plums, or seeds in a watermelon, basically spreading the mass evenly throughout the entire structure. Section 3. Rutherford's nuclear model.
Now, Thomson's model was definitely elegant, but you know how science works, you need experimental proof. Enter Ernest Rutherford and his students. They devised an experiment to put Thomson's pudding to the test. They took a wildly thin piece of gold foil, we're talking just 100 nanometers thick, and shot high-energy positively charged alpha particles straight at it. Based on Thomson's model, that positive mass was soft and spread out evenly. So Rutherford fully expected these heavy, fast-moving alpha particles to just blast right through the foil with barely a nudge. But the actual results? Absolutely mind-blowing. While most of the particles did pass straight through, about 1 in 20,000 experienced this massive repulsive force. They didn't just deflect a little, they bounced straight back toward the source. Rutherford famously said it was as if you had fired a 15-inch naval shell at a piece of tissue paper and it came right back and hit you. No way, right?
This single, shocking observation totally destroyed the plum pudding model. I mean, Rutherford realized right then and there that the positive charge and the mass couldn't possibly be spread evenly. The only physical way an alpha particle bounces straight back is if it hits something incredibly heavy and unbelievably densely packed. Rutherford concluded that the atom is actually composed mostly of completely empty space, with almost all of its mass and positive charge concentrated in a terrifyingly tiny, dense center, the nucleus. To really wrap our heads around the staggering scale we're talking about here, the source text gives us this phenomenal analogy. Imagine the nucleus of an atom is the size of a cricket ball, sitting right in the middle of a field. If that were the case, the outermost edge of the atom, where those electrons are orbiting, would be 5 kilometers away. The radius of the whole atom is roughly 10 to the negative 10th meters, while the nucleus is a microscopic 10 to the negative 15th meters. It is almost entirely empty space.
Section 4. Atoms by the numbers.
Before we tackle the major flaw in Rutherford's model, and oh, there is a big one, we need to quickly categorize all these newly discovered subatomic pieces. So the positive charge in the nucleus comes from protons. And the number of protons, which we call the atomic number, strictly defines what element you're looking at. But the nucleus also contains neutral particles called neutrons. This leads us directly to isotopes. Isotopes are atoms of the exact same element, meaning they have the same number of protons, but they have different numbers of neutrons. Take hydrogen, for example. It always has 1 proton, but it can have 0 neutrons, which is protium, 1 neutron, deuterium, or 2 neutrons, tritium. And because chemical behavior is driven entirely by the electrons, which just match the protons, all these isotopes react identically in chemistry.
On the flip side of that, we have isobars. These are atoms that have the exact same total mass number, meaning if you count up all the protons and neutrons together, the total is identical, but they have completely different atomic numbers. A really great example is carbon-14 and nitrogen-14. They weigh exactly the same, but one is a carbon atom and the other is nitrogen.
Section 5. The nature of light.
All right, so here's the crucial point. Rutherford's planetary model of the atom, with the electrons orbiting the tiny nucleus like planets around the sun, was brilliant, sure, but it had a catastrophic, fatal flaw. Unlike planets, which are electrically neutral, electrons are charged particles, and according to the rock-solid classical electromagnetic theory developed by James Clerk Maxwell, any charged particle undergoing acceleration, and by the way, moving in a circle is constant acceleration, must continuously emit electromagnetic radiation. If that orbiting electron is constantly emitting radiation, it's constantly losing energy. The calculations actually showed that Rutherford's electron should spiral and crash into the nucleus in just 10 to the negative 8 seconds. Basically, matter as we know it shouldn't exist. So, to save the atom, scientists realized they had to figure out the very nature of light itself.
Now, Maxwell had already proven, back in 1870, that light is a form of electromagnetic radiation. It acts as a wave of oscillating electric and magnetic fields, traveling through a vacuum at the absolute speed limit of the universe, 3.0 times 10 to the 8th meters per second. We characterize these waves by their wavelength and their frequency. But here's the thing. Classical wave theory was about to hit a massive brick wall.
Section 6. The Quantum Revolution.
As we roll into the dawn of the 20th century, classical physics is utterly failing to explain what scientists are actually seeing in the lab. And the breakdown really started with something called blackbody radiation. Think about heating an iron rod in a furnace. First it glows dull red, then it gets whiter, and eventually it glows blue as it gets unbelievably hot. The intensity and the color of the light change based solely on the temperature. But classical wave theory predicted something completely different. It literally couldn't explain why the light didn't just infinitely increase in intensity at shorter and shorter wavelengths.
Then, in 1900, Max Planck comes along and proposes a radical reality-bending solution. He suggested that energy isn't some continuous flowing wave like a smooth ramp. Instead, it behaves more like a staircase. Energy exists in discrete, indivisible little packets called quanta. You can stand on step 1 or you can stand on step 2, but it is physically impossible to hover in between the steps. The energy of these specific packets is calculated by his now famous equation E equals hv, where h is Planck's constant. Basically, the universe is fundamentally pixelated. And this whole particle-like behavior of light was totally cemented by the photoelectric effect, which Hertz discovered back in 1887,
When light strikes a metal, electrons get ejected from the surface. But strangely, if you blast the metal with an intensely bright red light, absolutely nothing happens. Yet, a very dim blue light ejects electrons instantly. The overall brightness didn't matter at all, only the specific frequency mattered. Light was acting like discrete particles, which we later called photons, colliding with the electrons on a one-to-one basis.
Which brings us right to the edge of modern physics, leaving us with a seriously provocative question. If energy moves in these rigid, discrete steps rather than a continuous, smooth flow, how exactly does this quantum weirdness save Rutherford's spiraling electron and keep the entire atom from collapsing in on itself? The clues are actually all right here in the experiments we've explored today. How does Niels Bohr take this quantized energy and use it to map the final structure of the atom? Well, that is a fascinating revelation you are definitely going to want to explore further. Thank you so much for joining me on this journey today on The Explainer. Keep observing and keep learning.